Welcome to this explainer. Today, we're jumping right into a seriously epic macro to micro journey through the cosmos. We're going to deconstruct the fascinating anatomy of Caldwell 90, an elliptical planetary nebula. The goal here is to peel back its layers and figure out the extreme, buzzing stellar engine hiding right at its core. It's a pretty incredible story full of cosmic disguises and chemical fingerprints, so let's get right into it. To get there, we're traveling roughly 7,270 light-years deep into the Carina constellation. Remember, when you look at the night sky, you're literally looking back in time. The light hitting our telescopes from Caldwell 90 has been traveling for over 7 millennia, just to bring us this story.
Part 1. Meet Caldwell 90, the cosmic onion.
Discovered way back in 1834 by John Herschel, Caldwell 90, which is also cataloged as NGC 2867, features this highly fragmented inner nebula, and it's surrounded by a really faint double asymptotic giant branch or AGB halo. Basically, these rings of ionized gas are just the shed outer layers of a dying star that were puffed out into space over thousands of years. So we kind of have to peel it back layer by layer, starting from the outside and working our way down into that blazing center. What's really wild here is just how asymmetrical that outer halo actually is. It bulges out prominently toward the north, but even cooler are these unique radial structures stretching way out into the cosmic void. Astronomers consider this one of the best examples of these features extending into a massive outermost halo. It tells us that the star's shedding process wasn't smooth. It was dynamic, uneven, and pretty chaotic. Part 2. A fiery Wolf-Rayet heart, the engine room. Okay, let's push right through that ionized gas and head straight for the core. Sitting at the very heart of Caldwell 90 is a Wolf-Rayet star, specifically a GW Virginis type. Now, what does that actually mean for us? Well, it means this star is a highly evolved, hydrogen-deficient powerhouse. It's also what astronomers call a non-radial G-mode pulsator. So basically, the star is wildly vibrating and pulsating every 768 seconds. It's essentially this bare, exposed stellar core just throbbing out there in the dark. And it is unimaginably hot. For a long time, the estimates were all over the place, but modern analyses using some really sophisticated stellar atmosphere models have bumped this star's surface temperature up to a blistering 165,000 Kelvin. To put that into perspective, our sun's surface is just under 6,000 Kelvin. So yeah, it's that extreme heat that's ionizing the surrounding nebula and making the whole thing glow. But here's the great mystery that had researchers totally scratching their heads. Despite that 165,000 Kelvin heat, the star is surprisingly missing the powerful stellar winds that astronomers usually expect to see. Normally, researchers look at spectral data for specific signatures called P Cygni profiles, which point to violent, fast-moving winds blowing off the star. But for Caldwell 90, those profiles are either mysteriously weak or just completely absent. So we hit a major hurdle. If we obviously can't fly a probe 7,270 light-years to physically sample this thing, and its stellar winds, which usually broadcast its chemical makeup, are completely quiet, how do we decode its chemical history? Like, how do we actually know what it's made of? Part 3. Decoding the ultraviolet spectrum down to the subatomic level. To solve this, scientists had to rely entirely on light, zooming all the way in to the subatomic level. Highly complex UV spectra captured by the IUE-infused satellites act like a literal topographical map of the star's atmosphere. They represent over 80 distinct emission features. Every single one of those jagged peaks and valleys is a specific element absorbing or emitting ultraviolet light at an exact wavelength. It's basically the ultimate chemical fingerprint. And by carefully reading that incredibly complex data, scientists discovered something amazing: a massive overabundance of neon. Specifically, the highly ionized NeVIM emission line revealed a neon mass fraction between 0.01 and 0.04. In the grand scheme of stellar chemistry, that is a highly specific and extreme chemical fingerprint that helps tell the story of the star's entire life. It gets better. The spectral data even lets us calculate the exact physical properties of the gas. By looking at specific diagnostic lines, like the doublet of NeVI, researchers calculated an electron density of log Ne equals 3.9. This takes those abstract light squiggles and grounds them into the physical reality of an incredibly dense, buzzing stellar atmosphere. We are literally measuring the density of a gas cloud thousands of light years away just by observing how it manipulates light. How cool is that? Part 4. A normal nebula, extreme engine, contextualizing the cosmos. All right, so we've got the temperature, the chemistry, and the density. When we pull back and compare Caldwell 90 side by side with another planetary nebula known as PB6, it sets up a brilliant cosmic juxtaposition. Both of them share that exact same extreme 165,000 Kelvin temperature, and they have similar Wolf-Rayet central stars. But when you look at the progenitor type, meaning the original star that created the nebula, they come from totally different origins. Unlike PB6, which is heavily enriched in helium and nitrogen, which is a classic sign of a massive heavyweight progenitor star, the chemical verdict for Caldwell 90 is entirely different. Its halo only shows carbon enrichment, with zero extreme nitrogen or helium spikes. In astronomical terms, this means Caldwell 90 has normal disk abundances. So the absolutely crucial point is this. Despite having this incredibly extreme 165,000 Kelvin Wolf-Rayet engine powering its core today, Caldwell 90 was not born from a massive giant. Actually, scratch that, it wasn't even close to a giant. It was a relatively low-mass star. Before it died, it went through a third dredge-up, an internal mixing event that churned carbon all the way up from its core to its surface. Then it just blew off its outer layers, giving us the nebula we see today. Looking at the timeline of how we figured all this out is pretty incredible. Our understanding has evolved from a simple blurry smudge spotted by John Herschel way back in 1834 to the early UV data in 1979, all the way to highly precise subatomic satellite data that gave us those revised 165,000 Kelvin temperature models in 2014. Bit by bit, technology has let us literally peel back that cosmic onion. As the source researchers noted themselves, the sheer complexity hidden within this single microscopic point of light in the Carina constellation is just staggering. What looked like a tiny dot in the sky turned out to be a pulsating, hydrogen-deficient, neon-rich furnace, all wrapped up in an asymmetrical, radially structured halo. The grand takeaway from this explainer is really a masterclass in cosmic disguises. We've learned that stars with completely different initial masses and entirely different life histories can end up wearing the exact same fiery Wolf-Rayet disguise at the very end of their lives. You simply cannot judge a star by its final temperature. You absolutely have to read its chemical fingerprint. Which leaves us with one final, mind-bending question to ponder. If the universe is this good at masking the true origins of stars, perfectly disguising a low-mass star to look identical to an extreme, heavyweight giant, what other spectacular illusions are hiding right in front of our telescopes? Keep looking up and always keep questioning what you see.